Lecture 9, Part 2. In the previous section, we have seen numerous types of hot and cold utilities that we can provide to our chemical process. However, the infrastructure that is needed to provide those utilities can be extensive and costly. Okay, as you can see here, so this is a typical steam system, and here we can provide different levels of steam: high pressure steam, medium pressure steam, and low pressure steam to provide as a hot utility to our chemical process. And this consists of a boiler, and obviously we burn fuel in this boiler, and then the feed to this boiler is our treated water, clean water that we actually feed to this system, and then by burning fuel we actually heat it till the steam starts to come out of this system. And we require fuel, as I said, to operate this system, and the amount of fuel that we need per unit of mass flow rate of the steam can be variable and obviously contributes significantly to the overall operating cost of this chemical process. Okay, and here we can have different types of steam. So obviously we first produce high pressure steam, and this high pressure steam can be provided directly to satisfy the heating demands of our system if we require high pressure, high temperature steam. Okay, but we can also provide low pressure steam or medium intermediate pressure steam if our process requires so. Okay, so this high pressure steam can be used to generate power, as we discussed in part 1. We can use this high pressure steam as feed to this steam turbine, and then we can generate some power, and then the exhaust of this steam turbine can be used at a lower pressure and a lower temperature, obviously lower than the high pressure steam, and this exhaust can be used to satisfy the heating requirement of our process. We can further reduce the temperature of this steam exhaust by feeding it to the second stage, and by doing that we again expand our steam, and in the process of expanding we actually reduce its pressure and temperature, and as such we can actually produce LP steam from the second stage, and that LP steam can be fed to our system if our system requires heating at that level. We may also use condensing turbines associated with our chemical process, and these condensing turbines, although produce power, they do not produce any useful heat from the process that can be used in the process. So it condenses the steam, and this condensed steam goes to the condenser where it is completely condensed, and then you treat this water for scaling or for any other cleaning purposes, and then you can either feed it directly to the boiler, or you can heat it slightly with the hot utility to increase its temperature, and then fed it to the boiler. Okay, so this is a complete cycle of a typical process steam plant. So a typical steam system such as this, it's very unlikely that it provides the requirement of a single chemical process only, although of course it can, but generally speaking, this typical steam system is used for a whole chemical processing site with multiple processes. Okay, so it is not only for one process, but actually for multiple processes on a chemical process site. Even the production of water required for the boiler requires a large amount of processing, as you can see in this diagram here. So we start with raw water or makeup water if we are returning system where we have some condensate return from our system, and it has to be treated in a number of ways before it is pure enough to be employed in a boiler. And pure water means less maintenance problem for the boiler, because if you have non-pure water, then you can have scaling, and it is very difficult to remove scaling from the boiler. And even after treating the water and removing all the dissolved salts and solids, we still have to pass it through a system here that is called deaerator. And we actually do that to remove the dissolved gases in the liquid, and for this purpose we use this LP steam. So LP steam get in contact with the water and take the gases out of this water, and this LP steam can be directly from the boiler, or this LP steam can be generated somewhere in the system as a cold utility. And after this deaerator, we still have to sometimes treat it further by adding some chemicals to make it suitable for the boiler. Okay, and then we fed this extremely treated water or pure water into this boiler, and then we burn our fuel to provide heat to this water, and then we have the production of steam. Sometimes we also have to remove some water from the bottom of this boiler, and that is called as boiler blowdown. And this boiler blowdown contains impurities in the water that have to be removed from the boiler. Okay, so perhaps when we say that we are going to provide HP steam heating as a hot utility for a chemical process, we have to actually understand that how complex system is required to provide that high pressure steam. Okay, and it is going to cost or it is going to require a lot of investment in terms of utility production system for a chemical process. And this complex process can be shown quite clearly here in this diagram, which is probably fairly typical of a utility system associated with a group of chemicals that require different forms of heating and power. And we can have our power derived from complex systems of steam turbines that use the steam produced by the boiler as a feed, and then it can provide us power, and in doing so also produce intermediate pressure and low pressure steam, and then this intermediate pressure or low pressure steam can be further used for our process heating. We can also have steam generation through this gas turbine here, where again the power can be generated, and in doing so we also have some exhaust that we can use for high pressure heating or generation of high pressure steam, and then we can also fed this high pressure steam into the steam main to provide our process with the heating requirement. Okay, so as you can see here, we have different forms of heat available in the form of high pressure steam, medium pressure steam, and low pressure steam, depending on the heating requirement of our process. And this complex process can be shown quite clearly here in this diagram, which is probably fairly typical of a utility system associated with a group of chemicals that require different forms of heating and power. And we can have our power derived from complex systems of steam turbines that use the steam produced by the boiler as a feed, and then it can provide us power, and in doing so also produce intermediate pressure and low pressure steam, and then this intermediate pressure or low pressure steam can be further used for our process heating. We can also have steam generation through this gas turbine here, where again the power can be generated, and in doing so we also have some exhaust that we can use for high pressure heating or generation of high pressure steam, and then we can also fed this high pressure steam into the steam main to provide our process with the heating requirement. Okay, so as you can see here, we have different forms of heat available in the form of high pressure steam, medium pressure steam, and low pressure steam, depending on the heating requirement of our process. Now, if we want to provide higher temperature hot utilities to our chemical process higher than the high pressure steam, we can use a fire heater or a furnace that can produce high temperature flue gases that can be used for our process heating, or they can be used to provide heat to the hot oil that can be used as an intermediate hot utility for our process heating. So the high temperatures are generated in these flames, and then the combustion gases that are produced radiate heat to this section here, and these sections contain the process fluid or the process stream, and this flame can actually produce very high temperature combustion gases, and as the combustion gases move up, they exchange heat with the process fluid. So first, as I said, that is the radiant heat by using radiation, and then when they pass up to this point, they come in contact with these tubes here, fin tubes, to increase the efficiency of heat exchange, and then the combustion gases, the heat from combustion gases can be taken by the process fluid in these tubes, and finally we have the combustion gases went out of the stack, and at this point where the combustion gas heat cannot be used further for process heating is what we call stack point or a stack temperature. It means that after this point all the heat that is available to combustion gases will be actually went to the atmosphere, and as such it will be loss of heat. Okay, so that is called the stack temperature, and this stack temperature is closely related with the dew point temperature of the combustion gases as well, uh, and we will be talking about these further as we go through these lectures. We can see that process on a simple temperature enthalpy diagram here. And here what we see here is our highest temperature that we can achieve in a furnace, and is known as theoretical flame temperature, and that is the highest temperature we can achieve by the combustion process. And these combustion gases, as we move down, these combustion gases actually provide heat to our process for our heating requirement. And once we get from this point to our stack temperature, that is the point where I mentioned that we can no longer use it to provide heat to our process, or we cannot extract heat from these combustion gases, but we still have to go from this stack temperature to the ambient temperature, because we cannot vent out the flue gases at this temperature because they are high temperature, so we are not allowed by law. So we have to reduce it to the ambient temperature. But all the heat that is contained in this section from the stack temperature to the ambient temperature is actually lost to the system, and that is why we call it stock loss. Okay, and because this heat actually was not provided to the system and actually was wasted. So from here to here, these combustion gases are actually providing the process heating, while this section from stack temperature to this section, that is actually not providing any process heating. But when we are calculating the amount of fuel that is required for the production of the process heat, actually we have to take from here to here. Okay, because although we cannot use this part for production of or for our process heating, but we still have to account for the fuel that would be required to actually generate this amount of heat from here to here. Okay, and the slope of this line, or the relationship between theoretical flame temperature and the stack temperature, actually determines what would be the amount of fuel that we required, and we can calculate by taking the slope of this line. So it is understandable that if the theoretical flame temperature is higher than this point, if you increase it here, the slope will be different, and then you will have a different flow rate of the fuel. And by increasing the theoretical flame temperature, you actually reduce the fuel requirement, because if you have higher critical flame temperature, the slope will be actually higher, and then as such you will have much lower stack loss. But if you have a lower critical flame temperature, you actually increase your oil fuel requirement because you will have a much higher stack loss. Okay, and we will be talking about that this relationship or the amplification of this in the next lectures. We can also use hot oil circuits, and as I previously mentioned, we can use a furnace to heat up this oil. So the hot oil at a low temperature is provided to this furnace, and we heat up this oil by using flames or combustion gases, and then we get to a high temperature. That would be the T supply of the hot oil, and then this hot oil is provided to the system at temperature T supply, and then it gives heat to the process stream, and then in that process of giving heat it cools down, and then the hot oil is returned back to the furnace for reheating at a temperature called T return. Okay, and that's how the cycle continues. So if you now look this process on a temperature enthalpy diagram, we can see that the hot oil is provided at a T supply temperature, and as it goes from T supply to T return, it loses heat, and this heat is transferred to the process, okay, to meet the process heating demand. And the value of this T return is in control of the designer, so that will be you guys who can decide what T return you want. For both the values of T supply and T return, there needs to be at least delta by a delta T min above the process stream temperatures. Okay, so the value of T return will dictate what is the hot oil flow rate, and that will be the slope of this line. Okay, obviously you can operate the system at the minimum flow rate, but you can do that by only reducing the T return. Okay, and as I said that we can reduce the T return up to a level where there is at least the difference between the process stream and the T return is 1 delta T min. But we will talk about these relationships in much more detail in the coming lectures. We also briefly mentioned refrigeration systems as a mean of providing cold utility to our chemical process. Again, these can be extremely complex, as you can see here. So this system here is a compression refrigeration system, and it is actually providing refrigeration to two different temperature levels, level 1 and level 2. And we apply two different compressors for level 1 and one for level 2. Basically, our system comprises of a series of expansion valves here and here, and the liquid that is at high pressure expanded through these valves, and in doing so, the refrigerant cool to appropriate temperature to meet the cooling demand of the process. And the heat is extracted from the chemical process by this refrigerant, and this refrigerant then evaporates, and these vapors are then fed to the compressor. Okay, and then this compressor actually again increases the pressure of the liquid, and then this compressed liquid goes through the condenser that actually completely condenses the liquid at high pressure, and then after this condenser you have the liquid again that then passes through the expansion valves again, expand, become cold, and then again extract heat, and then go through the compressor and the condenser. So this is how the cycle continues. Okay, so this is again a complex process depending on how many levels or temperature levels we need to provide the refrigeration to within our chemical process. So in summary, we can see that we have hot utilities and we have cold utilities, and we can use these hot and cold utilities to provide the heating and cooling demand of our process. And there are various utilities associated with both hot utilities and cold utilities, and it is up to the engineer, that is you guys, to decide if they are going to use what level of hot and cold utilities and what combination. So for example, are you going to use one utility only, or are you going to provide a combination of utilities to supply the process heating and process cooling demand? Okay. Utility is normally associated with different costs, and it is the cost of the utilities that will actually help us determine the combination of utilities that we are going to use. Okay, so if you are going to use one utility, or if you are going to use a combination of utilities. And the choice of utility is actually an important part of process design, and we will see in the next lectures how we can actually look at utilities and also what they are required for, and helping us to make that particular choice. And we want to make that choice so that we minimize the overall cost of utilities that we have to supply for heating and cooling purpose of our chemical process. So that is all for this lecture. See you in the next lecture.